Alright, welcome back. This is Thermodynamics Homework Solutions for a Thermodynamics 1 course. This is homework number 7, which is mainly on entropy, but also kind of molecular perspectives of entropy. And I figure, well, we know about entropy, we can talk about Gibbs free energy. And so that's what this problem is involved with, is Gibbs free energy. Specifically, is a process spontaneous? What makes a process spontaneous and why? Okay. So what the problem is saying is, okay, you go to the grocery store and they have the oil and vinegar salad dressing you love, okay? And it's always what? It's separated. When you go and buy that bottle, you've got some water, you got, your vinegar down here, and you got your oil on the top, okay? And so you shake it up, and you pour it on your salad, and you put it in the fridge, and then you pull it out, and what does it look like? It looks like this. Now, we know that mixing is always entropically favorable. That usually when you mix things, they stay mixed. So why does this not stay mixed? Okay. What is the driving force, and why? Okay. So, the first question we ask is, does this happen? Is this spontaneous or not? Do I need to put energy into the system to have this happen, or does it just happen? Well, we know it just happens. We've seen it happen. So yes, it does happen. So it's driven by enthalpy or entropy, or both, but not neither. Okay. Now, the next question is, okay, what about entropy? Are the microstates becoming more? Is it becoming more chaotic? Do I have more configurations? That kind of thing. Well, if I think about this being the final state, and this being the mixed state, okay, and let's draw some molecules in here. Okay, now vinegar is basically acetic acid, but it's also just kind of water, So we're going to draw it like that, and then, here, just oil on top and water on the bottom. Now, do I have more microstates? No, I do not have more microstates. Okay. Now, one explanation, which is kind of simplistic and it's okay, but it needs more, is, oh, well, you have unmixing, and mixing is always entropically favorable. Yeah, but how is mixing entropically favorable with respect to configurations? And that's what I'm really kind of trying to drive home. Okay. What you have is you have water and you have oil, and there's only certain places they can go. There's only, if you kind of think about this as a lattice or seats in a room, you're saying, okay, water, you can only be down here. Oh, and oil, you can only be up there. Whereas here, well, you can really sit wherever the heck you want. Okay. So we've limited where that water can go, and we've limited where that oil can go. So the entropy definitely is bad. Now, what does that mean? Is it going up or going down? Well, entropy being bad is going down. Okay. So it's not driven by entropy. It's driven by something, so it has to be enthalpically driven. So it's definitely enthalpically driven. Okay. Which means the entropy has to be going down. But now we need to ask ourselves the question of why. So enthalpy going down means better interactions. Okay? So I have better interactions. Why in that case do I have better interactions than in this case? Okay? Well, I have to think about interactions. And so, okay, we have van der Waals, we have this, we have that, and same thing kind of over there. But what is going on here? The oil is getting in the way of the water. The water wants the hydrogen bond. It has these polar, interactions, and it wants the hydrogen bond, but these filthy oil particles are getting in the way, and it can't hydrogen bond very well. And so basically the water says, get out of here. The oil says, I don't care. I still get, see, the oil only interacts with van der Waals, so as long as it's touching something, it's happy. But the water is not happy, so it kicks it out. The oil pretty much stays the same, but the water is so much happier having kicked it out. Okay? Because now it can maintain hydrogen bonds. And that's kind of why I say, oil's not really hydrophobic. The oil could care less. It's happy either way. The water's xenophobic. Water doesn't like anything that doesn't have polarity or hydrogen bonds, or if it's not like water, it doesn't like it. And so, I don't like the term hydrophobic. I like the term xenophobic for water, but it's such a water-centric world we live in, that's just how it's going to be. But the reason why the enthalpy goes down is because I have more hydrogen bonds here than I do here. And that's really what it boils down to. No pun intended.